Okay. Okay.
Take it away.
All right. Wonderful. Wonderful. I have to give an excuse. This is a hollow ground with many famous formulas being written on this whiteboard, and so Shafi said it's the end of the workshop. People are fried. Entertain them with some pixels, and that's what I'm going to do. There's also going to be a story. The story will have nothing to do with animal communication, but maybe, just maybe, there might be something that you guys can take from my experience in computer vision, and maybe it will click something. Let's hope. If not, then just enjoy the pixels. Okay. Okay. So I did my PhD in computer vision, and this was more than 20 years ago, and the world was very, very different. I had more hair, but also the way that we did our work was not really very focused on the data. And in fact, the typical CVPR joke of the time was, if your paper has one image, it's a hack. But if it has two images, it's an algorithm. And if it has three images, oh, it's a framework. So really, and in communities, learning communities like NeurIPS, for example, this was even more so, that the primary thing was the learning algorithm. The learning algorithm was the key. That's what you come up with, this brilliant idea. This is what your advisor will be happy for you, and then you write it all up and you work on it for half a year, and then maybe a week before the deadline you add some, use some features, and then maybe the night before the deadline you say, okay, yeah, I need to run it on some data, some UCI mushrooms, if anyone remembers that, right? Something, right? Doesn't really matter. Okay, so data really got no respect. Okay, and fundamentally, I think this was always wrong, but I think it took our field a very, very too long a time to appreciate, because the signs were already there. So this is an example from, maybe some of you have taken a computer vision class, maybe. So you might remember this. The first time that face recognition actually worked. There was a time it didn't work at all, and then boom, suddenly it started working. And then the next few years, it was in all the cameras, and just big success story. Can anyone who took computer vision or machine vision class remember what was the paper that made that big leap? Yes? Thank you. Ah, wonderful.
Face detection. Face detection.
Sorry. Yes. So face detection. Yes, that's correct. Okay, that's correct. That's what everyone remembers. Viola and Jones. But actually, it wasn't the first, and it wasn't the best. There was a set of papers that came out basically around the same time that just started working. Okay, and the first one was Raleigh Baluji Kannadi, the second was Shahriar Kannadi, and then the third one was Viola Jones. Raleigh Baluji Kannadi was the first, Shahriar Kannadi was the best, Viola and Jones was real time. Okay, but that time Shahriar Kannadi was also real time. So that's not really the reason. What is the reason that everybody remembers Viola and Jones? Look at this. The features that Raleigh used were pixels, boring. And the classifier, oh my God, neural networks, that's so 80s. That was just old school. Like nobody wanted to hear anything about neural networks in the 90s because it was just really old school. Shahriar Kannadi, okay, features were a little bit better, pairs of wavelength coefficients, but naive Bayes, so naive. Viola Jones, okay, features were hard, pretty good, but classifier was this boosted cascade, and this beautiful algorithm, absolutely gorgeous. I still teach it in the machine learning class because it is a beautiful algorithm. But guess what? Completely different features, completely different algorithms, pretty much the same performance. So why do you know what was actually the unifying theme between those papers that made them work?
Data set.
Huh?
Data set.
It was the fact that they were the first ones to realize, oh, maybe not, we shouldn't just use positive data of faces. Maybe we should also use data with no faces, negative data. That was what all these papers had in common. But somehow in our field, that did not get recorded. That simple idea did not actually get recorded. Why? Well, because unfortunately, there is this scientific narcissism. You know, we love to give credit to our own cleverness because, you know, data is out there. Data is just physics, just laying around. It's like it's not fair to give credit to it. The credit is to our cleverness. And I'm going to try to convince you that this has actually been kind of setting us back for a while, and we should basically become a little bit more humble. Okay. And there is a wonderful paper. It's quite old by now, but I think it's still quite relevant. It's called The Unreasonable Effectiveness of Data from folks from Google. And it's basically, the argument is that, you know, parts of the world are explained by elegant mathematics, you know, physics, chemistry, astronomy. And we have done really, really well in all of those. That we have really made great progress. But some fields, it's really, really hard to explain it by elegant mathematics. Psychology, genetics, economics, linguistics, AI. Huh?
There's a difference between saying it's hard and saying it cannot.
No, that's right. That's right. It hasn't happened yet. Let's put it that way. Okay. I think they do say it cannot. They take it more argue. Yeah, they take a stronger argument. I'd say it hasn't happened yet. And this is what they argue. This is where the magic of data comes in. And because, you know, some things are just messy, and the closer you get to kind of evolutionary things, the messier it gets. You know, if you're in the world of physics, you know, things are good. If you're in the world in biology, then the entropy gets really hard, right? So like you take something like a Navier-Stokes equation, and it's a very, very complex process. So this is like the computer graphics person and me talking, you know, rendering this beautiful smoke. Okay, it's not easy, but it's actually mathematically, it's, you know, it's just the Navier-Stokes equation, and you just need to, you know, run it the right way, and then you get this beautiful, beautiful smoke. But try rendering the bark of this tree. Very, very hard. It's an extremely hard problem. Even now in video games, you know, this kind of things like natural things like bark on trees doesn't really quite look realistic. Why? Because there is just way more parameters here, because the appearance of this bark of this tree depended on, you know, the genome of the tree, all the entropy of the evolution of that tree, plus whether, you know, squirrels lived there, which latitude, longitude the tree was, you know, what were the weather conditions before, right? There is just lots and lots of data that goes into this appearance. And so it's not as easy as, you know, picking a few parameters to get it there, okay? And even, you know, defining things like a tree it turns out to be pretty hard, right? So, you know, brown trunk moving upwards and branching with leaves. Okay, that's not quite gonna fit. It's going to fit many other things that are not trees, and it's also not going to explain some of the trees. And you know, if you want a longer version of this, Wittgenstein has a whole treatise on this, and Eleanor Roche actually here in Berkeley also wrote a lot about this issue, right? And yet, even though there is no good definition of something like a tree, every 3-year-old can tell you a tree from a non-tree, right? Because of the data. Okay. And the nice thing is, of course, that now we have this deluge of data. In fact, we have it for a while. So even while this has been a problem in the past, that we just did not have the data, now things are changing. Okay. And what we have seen, you know, maybe even starting 20 years ago, some of work I did, and also Antonio Torralba, my dear colleague, was showing that if you have enough data, then some really, really dumb algorithms could work surprisingly well. Okay, so this is actually a paper from Antonio, who I understand couldn't make it, but don't you worry, he is here in essence. This is This is something that that they did really early on, 2008. Okay, way before like a lot of other efforts like ImageNet. Basically, Antonio asked and co-workers asked, how many images does a 5-year-old see? And they came up with a number that's big, but it's not that big, 80 million. Even in 2007, you could actually deal with 80 million images. Now, the only trick is that you couldn't store them in high resolution. You had to store them in small resolution. So they realized that actually, if you store them 32 by 32 pixels, you actually get a lot of the information in there. And so this was a data set of 80 million 32 by 32 images. For those of you in machine learning, maybe you remember CFAR 10, CFAR 500. That is just a tiny sliver that they scraped from that data set. Yes?
But the tiny images, it's not a bug, it's actually a feature because of the small size. The nearest neighbor problem doesn't suffer. Well,
that's right. That is true. That is true. That is true. It was, yeah. I mean, I would still love to have them bigger because you can always make them smaller. In fact, that phase detection algorithm, the first thing they would do is that actually make the images smaller because then it would actually work better. So I would have still liked it to be higher resolution, but you're right that actually reducing the dimensionality often is helpful to you. Any other? I do want to have this interactive, so please interact. Okay. It kind of magic started to happen. So this is just examples of a few images. This is 3 images, and these are their nearest neighbors, the closest images in L2 sense, I think L2, to those. And then what you can see is that, if you have like 8,000 images, you already get like most of these are humans, and most of these are like outdoor scenes. But as you get more and more data, they just get closer and closer and closer, right? There is this kind of postmodernist sense that, all the images actually already have been captured. You just need to find it. And they were able to, they had before ImageNet, they had mapped this to WordNet. And so they could actually use those nearest neighbors to get you kind of a WordNet hierarchy and explain an image in terms of the labels of the WordNet hierarchy. And even without any annotations, they had these beautiful results for example, for colorization. So you give the system a black and white image, and it colorizes it for you. And the way it does it is basically it takes, I think, like 9 or 15 nearest neighbors and averages their color. And you can see that it's doing it in a very data-driven way because this guy colorized correctly, but this guy did not, because there is just not enough data that is upside down. So this did not give you the right signal, but this did. Okay. And again, this is the simplest algorithm in the machine learning textbook. This is nearest neighbor, right? Which of course is not that bad. Cover and Hart says that it's very close to Bayes' risk. So it's not bad, but it's a very simple algorithm.
Sorry.
Yes.
Okay. Can you, I think I understand what a nearest neighbor is based on context, but I think I'm interested in understanding how human programs the thresholds for what counts as a nearest neighbor.
Nearest neighbor, right. So nearest neighbor is the you have a set of points in n dimensions, and then for your query point, so this is, let's say, your query point, you find the closest point in something like L2 distance. Like Euclidean distance, for example, that's the simplest one. There are other distances you can use, but the L2 distance is the simplest one, and that was most people use. So this is nearest neighbor. It's the first algorithm you are taught in the machine learning class, and I claim that it's still the best. There is also a little bit better version of it. It's called K nearest neighbors, where you take, instead of the closest person thing, you take K closest things, and then you average the labels of those K closest things, and that works even better. That's actually as good as Bayes' risk. You cannot do better than K nearest neighbor under various assumptions of things going to infinity. Okay. Yes? All right. So around the same time, I was also very keen on trying to see how far we can go with data, but I like bigger images. So I was thinking, okay, how about hole filling? So you have an image, took it in Switzerland, but I want to get rid of this castle, want to fill in this hole. What do? The same thing. We downloaded only 2 million images from the internet here, and basically again do nearest neighbor, and then a little bit of computer graphics, and voila, it does okay. And you can have second nearest neighbor, third nearest neighbor, and sometimes it doesn't quite work, but you can get rid of the view from get a better view from your window. You can get rid of all this build-up on your favorite beach, etc., etc. And so why does it work? And here the thing is, the story of this paper was that this was 2007. So again, the biggest data set was like 10,000 images, right? And so we downloaded 20,000 images in the beginning. And my then student, James Hayes, said, okay, it's not working. So these are the nearest neighbors for this image. And they are not really very near, okay? And so he was like, okay, you know what? It's Christmas. We're probably not going to make this, but I'll just keep downloading over the Christmas break. And then when we came back in early January, we had 2 million and exactly the same algorithm, the same nearest neighbor algorithm that we did before. Suddenly, the neighbors became much nearer. So it is indeed that sometimes, when you have enough data, it starts whispering into your ear. And this is not, lots of data is good, but as we all know, this is a very high dimensional space. So no matter how much you download, 2 million is really not that much. There is other things that are going to help us out. Here is an image, and I want to get rid of the screen. Okay, so I get rid of the screen. Now I need to fill it in, and it does very well. Let's look under the hood to see what's happening. Here is the nearest neighbors. And here is the first nearest neighbor, the closest image. So look at this. This is a different river, a different city. Okay, but we have two things going for us. Thing number one, we as tourists are very boring. I cross the street or across the Seine and I turn right. And, oh, what a beautiful view. Say I and 10,000 other American tourists, right? So we are biased in the kind of pictures that we take. Also, European architects are also maybe don't have that much imagination because, oh, you have a river, let's bank it up with granite and let's have some high buildings on the side because we want to have them. They all want to have nice views into the river, right? So those two things make the problem actually not as terrifying as it could have been, because the distribution of these photographs on the internet actually lives on a lower dimensional space than one would have thought. Okay, and this is why it works. Later on, we the next year, James and I also apply this to this cute problem we called IM to GPS. So you give us an image, and again, we had, by that time we got 6 million images, and they all had GPS tags. And again, we just did nearest neighbors, and voila, it could basically geolocate our query image. Not badly. I mean, it wasn't like perfect. It wasn't CIA quality, but it was not bad. Okay, and this is 2008. Interestingly enough, fast forward 15 years. Yes.
There's something, so like thinking about this, like learning, there's something not satisfying because it's memorizing and not generalizing in a way. Or are you saying there's nothing left to generalize to? These are all the images that anyone could possibly take.
Yeah. So I would love it to be generalizing. Absolutely. Generalization is a very hard problem. I think where I'm going with here is that when we think something is generalizing, we need to really look carefully whether it's not just memorizing and how much it's generalizing, okay? Because over and over, we have been kind of whipped by this. We think that we are generalizing, but actually, it turns out, speaking of which, 15 years later, neural networks come in, okay? And the Google folks decide that they wanna repeat this task with their big neural network. And you gotta give them, the name is great. The paper title is fantastic, okay? And it worked much, much better, okay? But they changed two things. Instead of nearest neighbors, they had a neural network, I think BGG at that point, or maybe InceptionNet. But also, because they're Google, they had like an order of magnitude more data, okay? Unlucky for them, I was the reviewer, and I said, no. You need to have an apple-to-apple comparison here. You need to see how much is it the data and how much is it the algorithm. And guess what? So this is into GPS. This is James Hayes's hand-tuned features. And this is fancy schmancy Google, lots and lots of parameter neural network. And it's not doing amazingly better. It's better in some regimes, it's worse in other regimes, okay? Again, we have to be very careful to make sure that we know where the performance is coming from. Yes?
I thought you were gonna make them do nearest neighbors on 91 million.
I mean, that would be even better, but they did not. I mean, I told them apples to apples. They presumably just decided to do the easiest thing. But yeah, it would have been even nicer to do it the other way. Yes.
Have you tried?
No. I think it's still only because the bad thing about nearest neighbors is that you really have to linearly go for all of your data every single time. So it's very expensive, very expensive. So I'm not saying people should drop their neural networks and switch to nearest neighbor. What I'm saying is that under the hood,
It's very expensive in other measures, right? So
and storage too, yes. Yeah. No, it's not a practical method, but it's a very good baseline. It's a very good baseline, especially if you feel like you're generalizing. Maybe you should just double check that you really are doing better. Yeah. Okay. So the good news, really stupid algorithms for lots of data gets you this unreasonable effectiveness. Okay. But given the whole biological tilt of this workshop, surely brain not going to remember 80 million things. Surely. Well, here I'm going to show some slides that my dear friend Oliver lended to me, and this is some of her very old work. She doesn't show this anymore, but I think it needs to be known because it's such a brilliant piece of work. She asked the question of what is the capacity of long-term memory? How much do humans actually remember visually, right? And what we knew before that point was a study by Standing, who actually showed that capacity seemed to be pretty good. Basically, he showed the subjects 10,000 images, and they were able to recall if they seen this image or not 83% of the time, which was very surprising. Okay, but it wasn't quite clear how much were they remembering, because the images are very, very different, right? One was a beach, the other was a kitchen. So there was, it could have probably been enough to just remember like a couple of words about the image. You didn't really need to remember all the details. So it wasn't clear how much actual bits of data was remembered. Okay, and so this is where Odd said, okay, I'm going to do another experiment, but I'm going to do it on harder data. I'm going to do it on data where you have completely different objects. So this is basically matching the standing experiment. Different exemplars of the same kind of object and different states of the same object instance. Okay. And Odd is amazing because she actually put the experiment on a slide deck, and we are all going to do it now. This is going to be a real experiment here, but it's really, once you do it, you will really understand. Okay, so basically the task is you need to detect repeats. When something happens, when something is seen again, you have to detect it. So you're going to be clapping. You're going to clap if you see something again. Okay? Okay, are we ready? Okay, it's going to go fast, so be ready to watch. Okay? Okay, let's do it. Good. All right. So didn't force you to do it for six hours, but I think you're starting to get an idea. Then at the end, she would actually ask these binary questions. Which one did you see, A or B? A. Very good. Which one did you see? A. Very good. Which one did you see? B. Okay. Pretty magical. Okay. So the results are, so she replicated standing. In fact, she got a little bit even higher performance than standing did, but I think within more or less within error bars. But what about different exemplars? And so Odd asked all of her psychology colleagues, what would you expect? It's going to be, chance. It's going to be, the same. It's going to be half the performance. Well, now that you did the task, what do you think? What is going to be? What's going to be here? What's going to be here? How are the two other bars going to go?
So probably high in the example.
Oh, sorry.
Probably a show.
Oh, sorry. Didn't. Yeah. Sorry. Basically, it was almost the same, right? Which was an absolutely magical result. How many people have seen this result before from Odd? Okay, so I'm good. I think it's good that I'm showing this because I think this needs to be known. Yes.
So just to clarify, so the question is, how much can we memorize if we are shown something for a short time, or is the question more general than that?
This is a very, very specific question, right? This is not even, can you memorize it? This is even a more specific question. Can you tell if you have seen something before?
But standing, so the experiment by standing?
The same procedure, yeah.
Okay, because I was thinking like Chinese people memorize thousands and thousands of ideograms.
That's right.
To the tiny detail,
That's
to the individual stroke.
That's right. Well, we all do. You guys just did. Yes, absolutely. It's a little bit tricky. So there is some follow-up work when you ask people to actually draw what you remember, and that turns out to be a much harder task than to tell if I have seen it before. Okay, so these things are somewhat different, but I find this really, really impressive. So that really informed a whole bunch of the work I do, when I saw this result, because I think this is very telling. Yes. Sorry, I don't see well. That's why I do computer vision, so you have to just shout.
Do you have any knowledge of whether this is sense specific? That is to say, has anyone done this with touch or with smell or with hearing?
Good question. I mean, I know that for semantics for words, I think it's much worse. I don't think anyone has done it for other senses. You can email Aud and ask, or somebody should do it if not, because that sounds like a great idea. I think yes. I, as a vision person, half the brain is doing vision, so I would like to think that there's more parameters devoted to visual data. So I want to see that we're, vision is special in this case, but I don't actually know. I don't know. Yeah.
I'm really hopeful that it's the same things, just assigned to different modalities, because I got to tell you, I would have clapped like once. I couldn't do this stuff.
Oh, interesting. Yeah. So I mean, these are all averages. So yeah, I mean, people are different. Absolutely.
That you could do it with sequence of audio, though.
I'm really hopeful, because otherwise I better be.
Or maybe you were just not paying attention. End of the day. Well, okay. There's one more chance, because natural question here is: wait, do people have photographic memory? And for this, Aud did a follow-up study that, for some reason, they didn't even publish. But I think it's an even better study. Okay. What they did is they generated synthetic textures with the first and second order statistics of wavelet coefficients to match natural image statistics. Okay, so something like this. Okay, and then they run the same study, including these images. Okay, so let's do this. This one is short. Okay. All right. So as you can sense, it's basically the textures are pretty much a chance. So it's not about us remembering every single pixel. It's more interesting than that. We are remembering something that is on a learned natural manifold. Okay. So yeah, I think this is really cool stuff. So if you see Aud Oliver at some point, tell her that you saw this and she needs to publish this.
So yeah. It's interesting, but I'm not sure that I'm getting correctly the details, but basically what you said is that it's difficult for people in images to remember the details. So they would say that I've seen the image, but not the details. I think with words, it's actually the opposite. And there was, I think, the study in the Soviet Union in the 60s where people had a hard time to remember if they had a word in the sequence, but if you gave a definition, they would remember that. So, which is an opposite in
well, we know, but I think what I'm saying here is not that we don't remember the details. It's not about the details. In fact, remember how there were two TV remotes, right? That were very, very different, very, very similar, but you guys very directly picked the one that you've seen before. So the differences were very minute, and still you guys remembered very well. Here, it's not about the details. It's about these things being not on the manifold of natural images. They were not something that you perceive to be a sample from the natural visual world.
But if I asked you, have you seen a remote? I don't think that you would remember that. So if the question was, have you seen a remote, rather than showing a picture or two pictures,
right?
you probably
Well, cross modality. I think, I think this is happening on the visceral level. It's like a Rothko painting. You know, you remember a Rothko painting, but there is no way you can describe a Rothko painting, right? So I think there is actually no, it doesn't actually connect very well. Yeah. Other questions? Yes.
So to the point about the manifold of natural images, which I think is related to the generalization thing before, these are also like real photographs, right? And if, you know, the original example was dogs playing cards, and you can imagine lots of,
Wait, so these
sorry, no, not these, the things that people can recognize are all images of situations that actually, you know, objects that actually exist, situations that actually occurred. But there's this sort of intermediate category of things, you know, that are like Dali paintings or, you know, whatever, dogs playing cards that have natural image statistics to probably a higher order than this, but also would never actually occur in practice and have no nearest neighbors in any training set. So what does it mean to be?
Yeah, so that, we'll get there. There is indeed something about we are able to do some sort of a compositional generalization.
Because presumably those things are even more memorable than some random beach.
Yes. So, but I think what this, again, Owen does not have any argument what this means, and I'm not trying to say that I know what this means, but to me what this means is that things that we remember seem to be at least made up of things that we are familiar with. Whereas here, it is really not, it's not easy to see what are even the parts that are familiar. Yep.
I think also not so familiar, but also trained on. You know, nobody shows you a bunch of soil textures and so, mom doesn't show that, the parents don't show you.
That's right. In fact, you know, people who are, let's say, experts in mushrooms or, you know, experts in some, you know, geological rock patterns, they actually are able to recognize different parts that non-experts cannot. So this is definitely a trainable thing, absolutely a trainable skill. So I'm sure we can train some undergraduates of these things. But still, it's interesting that the untrained mind is basically allowing it to slip away.
As I was looking at this, in kind of introspection, as I was looking at these pictures, like I immediately recall the, you know, I think it's multimodality at play here, because I'm semantically, I heard words as I saw these pictures inside, whereas with these, I can't. I mean, even if remote are similar, but you can say, okay, your remote that looks like this, a remote looks like that. And here, I cannot even describe stuff. So I think the lack of multimodality, I mean, the lack of language recall that I have here, I think definitely, I mean, probably interferes with my results.
I'm not sure. There is some similar studies for pigeons. Pigeons are also very good at this stuff. So I wouldn't say, it's all language. Yeah.
Just real quick. So in the world of psychology, I mean, the studies have been done about encoding and how most people encode.
Right.
So visual is what we normally do. We get pictures of things, except for things that are more ambiguous, like this.
Yeah.
And I was wondering if you were hearing the words for that, because we have such limits on the number of words we can remember. And if you're trying to if you're encoding, you aren't hearing words though.
No, I was just, there's just all these pictures, and then like people are clapping, and I'm like, I don't know.
I mean, the 7 plus or minus 2 is much narrower than the visual aspect.
So the argument that you are saying is the naturalness of the scene, right? Rather than
you have to have seen at least parts of it.
You're arguing for chunking.
Yeah, small chunking. Yeah.
So since we're talking a lot about vocalization in this workshop, and if there is anybody's done a study about the sort of naturalness versus like doing this type of stuff with language versus or with sounds that are familiar to us versus, you know.
I can sort of answer a related thing. There's a guy at MIT, Josh McDermott, who was once in a vision lab, like a psychology vision lab, who then stole many techniques from vision and took them into the audio realm.
Mhm.
And I know one of the things he did was he proved that repetition in audio, after as few as 3, but by 5 repetitions of something, and where it's overlapped with other sounds, by 5 repetitions, we have it. And he did a thing similar to this, where he generated artificial sounds that had certain statistics which were similar to natural sounds, but which had never been natural sounds. And so he showed that just repetition of a thing a few times, even when it's mixed and overlapped with other sounds, is sufficient for us to extract it as a chunk and like, now that's a thing for you. So that's the closest study I can think of to this. I was hoping.
So Philip Pizzola and Odd Oliver had a few follow-up studies on memorability, which is basically how well do you memorize different instances, and they do show that the landscapes are memorized worse than objects and faces. But they did one study, and I don't remember the paper. I don't have it here. On doing the same for words, memorable versus forgettable words, because it turns out that there are some words that are more memorable. In fact, Odd wanted to do a startup where she would basically replace in your email the common words with the more memorable words, so that your resume or your email would that the professor would reply to you more likely. So look for Isola Oliva memorability language, that I think you should find that paper.
There's also like exemplar linguistics, and there's like these results, I forget who they're from, but things that like people have very good memory of like the gender of the last person they heard a word from, even like if that's not something that you would think you would log. So there is kind of like exemplar like studies in linguistics a lot, and I think there's people who really believe in that stuff. I forget who did those like gender studies, but it's really interesting.
I'm going way out of the limb here, but this is for both of you. I wonder if there's some notion of like consonance versus dissonance and how I might remember something. For example, I remember the opening measures of Purple Haze with that, with the tritone, right? Much, but the rest of the. I wonder if there's a visual equivalent.
So I think the atonal music is impossible to memorize because it is of the manifold of master music, right? Is that what you're talking about?
Sort of. I mean, immediately recognize it. Right. Maybe I don't memorize the particular pitches, but I immediately recognize something as consonant or dissonant.
Oh, I see. Yeah, I mean, the same way as if we ever get there, we talk about generating images. It's very easy to tell if something doesn't look like a natural image. Very hard for the computer, by the way, but very easy for us. And I think it's kind of the same thing. Okay, but I'm not like we don't have to. I don't have to rush for anything. As long as you guys are having fun, I'm your entertainment for this afternoon. So, whatever you guys want. Okay, so yes. So on one hand, nearest neighbor, data-driven methods, memorization seem to be a large part of what's going on. On the other hand, of course, raw memorization, if you just really try to look up from the data set what you have seen before, that's not going to work for a lot of issues, a lot of cases. For example, long tails, rare events, right? We as humans are able to deal with events that are rare, that we haven't really had the data for. We're still able to do it, right? So kind of this idea of disentangling different parts of our stimulus into chunks that are familiar to us, and compositionality, which is when you can recompose them back in ways that you haven't before, right? And of course, the latest generative model craze is really because things are starting to change, and it seems like we are now getting a little bit of a whiff of disentanglement and compositionality from some of these new generative models and the text models as well. But again, I'm a visual person, so I'm going to talk mostly about the visual stuff. Okay. So I'm sure everybody has seen this. Here is some dolphin for you. Dolphin is an astronaut suit on Saturn. Okay. And it's quite impressive because this is definitely something that has never been in any of the training set.
You're sure of that?
Yeah. Good question. We'll get back to that, but unlikely. This one is particularly happy with. This is DALL-E as used by a wonderful local artist, Danielle Baskin, and they were planning to take BART all the way to Marin, and that of course never happened. But this is DALL-E's imagination of what it could have been like to take the train across the Golden Gate Bridge, and to me, it's really, really impressive that it's able to merge together things that it has really not seen before in a very natural way. That's I find this quite impressive. But again, I'm a little worried because everybody's like DALL-E this, DALL-E that, stable diffusion this, stable diffusion that. We're always talking about amazing algorithm and then fancy language this, clip that, and then there's some data also, sure. So let's do our evaluation here again. So here is a prompt: squirrel reaching for a nut. These are 3 different approaches. Can somebody guess which one? Can you recognize any of those approaches? So this is 3 different algorithms using the same prompt. All right. Yeah.
Am I supposed to say like nearest neighbor versus?
No, they are all generative models, but they're all different generative models.
Different underlying, like is one a diffusion and one's like a tokenized language model?
Yeah.
Okay, I'll bite. To the left, I'm going to say it's a diffusion model. The middle one, tokenized language model. The right one, because you're just trying to fool us, is a nearest neighbor.
Ooh.
Oh, no. The right one's got a weird distorted case.
Okay, how about this?
So I'm going to say that's a style GAN. That's a GAN.
This one?
Yeah, I'm going to say the thing on the right is a GAN. The thing on the left is I'm going to say a tokenized language model. And the one in the middle is there to fool.
Oh, this is the tokenized one.
Yeah, and the one in the middle is there to fool me because it was actually a nearest neighbor that you threw into.
I see.
Yeah.
Okay.
I have a different. I think the right one is diffusion.
The right one is diffusion. Okay, and the other 2?
What can I choose from?
Okay, I'll give it. Make it easy. Okay, the choices are basically sequential model, diffusion type model, and GAN model. Middle one is GAN. Okay, and you said that the right one was GAN.
I think right is GAN. The rest is
All right, are you ready for the answer? Okay, DALL-E. This is a sequential model, basically LLM, which spits out pixels instead of words, and the latest GAN so
GAN, diffusion, and language model.
Yeah. So you got 100%. See, it's multimodal. But the point I'm trying to make here is they're very, very different models, right? Extremely different. But it's not obvious that you could tell one from the other, right? And in fact, this is a slide from my former student Taesung Park, who did the GigaGAN, which brought GANs back into competition. It's the number of parameters, basically the capacity for data. So now the young kids, they don't look at the data, they look at the number of parameters, but it's basically the same thing because it's the capacity for the data, right? It's like, in nearest neighbor, it's one and the same, right? Your size of the data set is your capacity. When you have a parametric model, then it's really how many parameters you have. But it's a function of data because you keep on increasing it until you run out of data, right? And so the bigger your model, the better your image quality. This is down is better, okay? And so you can see that the different methods here are basically all fitting that pattern. So like the sequential model that has smaller parameters is actually not so good, and the sequential model that has more parameters is doing actually very good. Okay. So once again, we might be getting too married to a particular, algorithm du jour, and not remembering this lesson again, that we need to look at the amount of data and of course the quality of data. And the fact that, yes, there is some really cool generalization, there is some really cool compositionality, there is some really cool disentanglement, but there is also a lot of kind of nearest neighbor-like behavior. So this is a synthetic image. I think something about lighthouse. I forgot the prompt here, lighthouse in a stormy night. And we have a method to basically trying to find some of the real images from the training set that are similar. And you can see that there is, very, very similar thing. There is still definitely some by parts compositionality that's happening, but it's not like complete magic, right? It's like it's not maybe super surprising that if given pages and pages of these, you can concoct something like that. Yes.
So I don't know. Well, probably it has been done, but an interesting experiment. So if you generate using one of these models a training set, and then you continue training on. So basically, there will be some kind of drift. Will this converge to some kind of stable point, and how would it look like? Will it be realistic images, or will it?
Wait, so you come. Oh, you generate. Oh, I see.
And retrain the model on generated images. Will it drift to something that will not look like natural images?
Frankly, I think that's already happening, because often we cannot tell if something is generated or not. I would venture to say that it's not going to end well. I think that it's very easy to fall off that manifold and go into crazy land. And this is why I'm also worried about, information on the internet. As we get more and more and more synthetic data, I think it will be very easy to go into crazy land.
But how will it look, the crazy land? What will it be?
It's just some local minimum, somewhere. Yeah, it could be, I think, arbitrary.
There's been some work on this recently where you lose the tails, basically.
But what you will see, for example, people with 6 fingers or things of this kind? Or?
You think that you'll eventually get to a fixed point of the Uber image?
No, but I will get images that maybe I can never see in nature, right? So something that.
No, I think that's what's going to happen. But I think it's not going to be one fix. I think it's going to be, there's infinitely many local minima, and I think you're just going to fall into one of them randomly. That's my prediction. Okay. Okay. 5 minutes. How about I show you? So you want to? Okay. How about I give you a choice? A paper with. Oh wait, I can give you a very quick because I feel like I should show some of my work, but very quickly. This is a paper that's going to be Exactly. Going to be a CVPR next week, and basically what we are doing here is we are instead of generating images, we're editing images. We're taking a real image and then we're giving it, the prompt is English language text that is an editing instruction. So instead of saying what should be there, we say swap sunflowers for roses, or what would it look like if it was snowing? Okay. And the idea here is really, if we had the training data, this would be a trivial supervised learning problem. Well, not maybe that trivial, but with modern diffusion or other generative models, it's fine, right? If we had input image, output image, and a text string, just throw it into the machinery and just crank, wait 2 weeks and it's done. Okay, and pay a lot of money to Amazon. But we don't have that data set. That does not exist. So really, this paper is really all about how do we get to the easy part? How do we prepare the data so that we can then hit the crank?
So you do not have supervised data set.
We don't. We don't have that data. Okay. Once we get this data, everything's easy. So the question is, how do you get the data? Yes.
Maybe not be enough data like that, but there's plenty of data matching that format on Photoshop forums on the internet.
Yeah. So I mean, when we talk about these generative models,
yeah,
hundreds or even thousands is not going to cut it. It needs to be couple of orders of magnitude. Yeah, we thought about this, but yeah, it was nowhere near enough, and it's also not general enough because Photoshop forms only shows things that Photoshop can do. Now, this is not really something that a Photoshop can do.
Well, the latest Photoshop that came out last week does exactly that.
That is true. Yeah. Okay, I'm not going to say, but because some of my former students are actually in charge of that project. But
yours is better.
No. Ours is earlier. Anyway.
Guess, do you use Clip for this?
No.
Okay.
Okay, have a guess? Guess number 2?
I don't have a guess number 2.
Okay. What's the most important? Okay? I think it's already here. Is it? No. Yeah. We use GPT. Okay. So and again, this is actually all my wonderful students and student postdoc Tim and Alex who came up with this very clever trick. They created some training data by hand, literally like a few hundred examples, input image descriptor, output image descriptor, and the edit that would go from input to output. Okay, here there's no images. This is just text. They just made up, or I think they took an input caption from a data set like lion or something, and then they say, okay, let's edit it and then write out what it would be as an output. Okay, so they wrote a few hundred of those, and then they said, okay, GPT 3.5, continue the pattern. Give me more of these things. And GPT-3 complied and just produced a whole bunch of more of it. Okay, the animation is going to be very slow. But yeah.
Can you go? Yeah. So isn't it sufficient to just give input and output, and then GPT can already solve for the edit line?
They felt that they wanted to, again, teaching by example is always better than trying to explain something in a more higher level thing. They wanted to have the feel of a kind of an image edit. And I think they tried this, and GPT did not really get the instructions that would sound right. But this is a little bit of fine tuning. This is just a little bit of example. It's like a few hundred of it. Yes.
But GPT is unaware of the image generation model that will be.
Yeah, this is just we opened up a window and they just start typing.
But then I imagine that you would generate images using these prompts, and do you actually know that it will look like what you asked for, or?
Okay, hold on, it's coming. Okay, so this is now we have the text, right? We have the triplets of the text. So again, these are the handwritten ones, and this is the generalization that GPT has produced, given input captions that we just stole from an image data set. We are not looking at images at all, just the text strings, okay? And some of them are actually nonsensical. Some of them did not work out. They try to filter them out, and then it turns out that actually keeping them as is fine. In fact, it was a little better if you don't filter anything, because more data is better, apparently, even if it's garbage. But then, how do we connect this to images? Well, there is a recent paper called Prompt to Prompt, and that paper is able to generate new synthetic images with related prompts that are themselves related. So you give it two prompts that are similar, but maybe with one thing changed, and they are able to generate images that are related. So these are not real images, they're synthesized. But there is a relationship between them that is exactly the relationship that we want. Okay? So now we have all our ducks in a row, because we are using GPT to produce from the input captions, the output caption, and the edit. Okay? Then we are using the input and the output captions into prompt to prompt to give us two images that is going to be the input image and the output image. And now we have our triplet. And now we are ready for some supervised learning, because we have the input image, we have the output image, and we have the editing prompt. And from now on, this is easy peasy, it's done. Okay. And here is an example. Make this a grocery store. You can kind of do multiple edits. You have different diversity. You can generalize to high res, put it in outer space. Humans, change humans into robots. You can chain the edits together. This is really my main contribution to this whole endeavor is this one figure that I'm very proud of. I'm particularly excited about how the Calder sculptures worked out, but I think also the claymation is pretty nice too. It can kind of hallucinate some 3D. It's it's very interesting. It's the biases are not just in the text; they're definitely also in the images. But it's kind of cool. And of course, it's not going to do magic for you. It cannot change the layout of the image has to stay the same. So it cannot zoom in, or it cannot like swap these people. And actually the language is the weakest link here, because the language is color the type blue. The tie and the blue are actually not binded together, although there's now work that's trying to improve that. Okay. Just a little example, we can also do this for 3D scenes using nerfs, where we can just edit the context in that. Okay, I think I will end here. So let's jump to the conclusion. And the conclusion is really, we should start to give data its due credit, even though it hurts us and our scientific pride, but I think it's going to be good for us long term. And the good news is that yes, data is necessary, and I think a lot of data will be necessary, but it's not sufficient. There is still going to be space and an opportunity for the flights of fancy and the creativity and the human spirit. So I think we'll be fine, and we'll have plenty of fun things to work on for years to come. Thank you. Any further questions? Oh, yes, sorry. Yes.
Yeah, thanks. This was great. One of the things I'm most impressed by is the related thing. One of the things I'm most impressed by is related to Alexander Calder. So I played a lot with Modigliani and in the style of Modigliani, and it's really impressive. And I think it goes beyond just like, I mean, impressionistically, it really captures his style. And I played with Stable Diffusion. But Modigliani had total of 200 paintings. And so what's your take on that? Like, I mean, data training is huge, but like you have this like few shot cases. Do you think that the kind of other styles that are well represented contribute to the ability of extrapolating from a style that is very sparsely attested?
Yeah. No, good question. By the way, this last paper, we have we have a demo online, and anyone could just go and play with it yourself. So you can try it yourself. My experience has not been so. I some of my favorite painters are Gustav Caillebotte and Hopper, and they're both, light is an important thing there, and I did not feel like, wow, it's really capturing it, but I think, even stepping back a little bit farther, if you want to think about it in terms of, art, like for me, there is art, and then there is artisan. The artisan and the artist are they have very different objectives. The artisan is trying to get something that looks beautiful. The artist is trying for something new. And so I feel that even though there is some sort of like a style of Modigliani, I feel like every time Modigliani was trying for something new, he was not trying to kind of replicate himself. He was trying, and it's kind of like the Malevich's black square, right? The whole point of the black square is that nobody has done it before. It does not make sense. The second black square is already not that exciting, right? I think that this is really where humans are still have plenty of space ahead of computers. That computers are very good interpolators, but they're not very good at moving forward and kind of expanding the boundaries.
Unless your instruction is do something new, and then give example. No, why?
Yeah. So there is a I think there is a little bit of too much hype on all of this. Like, it's not magic. This instruct. For example, there's this new Israeli company where they have a website where you can say, I forget what it's called, but it's like human or not. Like basically, it's like a Turing test where you're either talking to a human or GPT. And one of my students, Yossi, showed me it's very easy to defeat. You just ask the other person, give me a random number or say something random. And the computer just cannot do it. Just cannot do it, So I feel that is actually not that easy. And I have worked on creativity, computational creativity. So we try this, but it's hard. It's hard. Yes.
Since we're at Simon's, so it's a relative question, right? Because I think there's this thing, Aronson's oracle, which shows that if you can all go to it, you click one of two keys at random and it'll predict your performance at more than 75% within, I don't know, under a minute of you going like this at random.
I see.
Yeah. So it's a question of who's evaluating or who's asking.
Right. Well, yeah. Here it's the human evaluating the computer. Yeah.
Human can evaluate a computer, and a computer can evaluate.
Oh yeah, that's much easier. Yeah, computer. We are very predictable. Yeah. Yes.
So maybe taking a step back to the machine learning problem. So basically, your message is when we have a lot of data, then very simple stuff works probably the best, or at least can work.
We should try the simple stuff first before we get our egos too high. Yes.
Yeah. But so the question is, when we don't have a lot of data, like in our case,
yes.
for example, bioacoustics, so the data is very scarce by machine learning standards. What is the recipe in this case? So you need to assume a lot, right? Or you need to do actually sophisticated, fancy algorithms.
There is some transfer learning that seems to work quite well, actually surprisingly well. So a little bit of fine tuning on your data, plus a whole bunch of other data. So there is a work on visual prompting for analogies that they didn't have time to show. But what we show there is just a little bit of the right data can go a long way. But also, again, to channel my dear friend Antonio Torralba, if you don't have enough data, just try really, really hard to get more data, because that is the easiest, by far the easiest way. And your whales, they have seen or they have heard a lot of data, presumably, right? So at least evolutionary they have, right? So it seems like, if we want to compete with them, then you should get as much data as possible. Yeah.
Okay. Thank you for the nice talk. My question is, in this discourse, what is the place of data augmentation? Or in general, the question is, not all data is equal. Like, if we double our data set with just copies, this should not help. If we double our data set with copies with some noise, does it help? That augmentation show that sometimes help. Can we synthesize new data that is useful in an easier way than collecting new data? So this is the
right. So I'm in the anti-data augmentation camp. It's not a big camp; it's a very small camp. But I feel I believe in self-supervised learning. I don't want the human bias if I can avoid it. And data augmentation is human bias. You are kind of assuming, oh, these are the kind of changes, kind of transformations that will, or which I expect to happen in the data. Well, then you are basically only, preparing for what you expect. You don't prepare for the things that you don't expect. And we have seen that if you can really deal with a lot of data, if you can take in huge amounts of data, then you don't need data augmentation. Now, you could say, well, for this particular problem, I don't have enough data. But I feel like the reason that I think that transfer learning, training on some data, then fine-tuning on other data, seems to work surprisingly well, is because of the nature of our world. That our world and the world of other animals, and maybe even the world of animals who live under the water, it's the same, a lot of the same physical constraints apply. And so it seems like if we capture some of those constraints in data that maybe is not even that related, it feels like it should help. And I feel like it should help more than trying to imagine the kind of transformations that you expect should happen. So I'm all for just trying to get as much data as possible, even if it's just very different data, but still real physical data from our physical world, and see if that can help you. But if that still doesn't work, sure, you can do data augmentation. But I see a brilliant, glorious future when we will not need data augmentation. Yes.
So I guess even with really large amounts of data, there's always the problem of long tail, right? Like you also put that up on your slide. And that, I guess, cannot be solved with collecting even more data, because then it'll just be a different set of, a different subset of your data that will fall under that.
Well, the thing with long tails is we think we humans are so good at the long tails. But of course, we're only good at the things that we know we're good at. There must be so many things that we're really, really terrible at, but we just don't know that we're terrible at it because we don't notice it. So I think that the kind of long tails we are good at are in the, what's the opposite of the long tail? The fat middle? I don't, is that the, yeah, but parts of it are, I think, in the fat middle. I think the long-tailed, some very unusual things are still made up of the more usual things. So I think with the right compositionality, I think we can kind of map it back into the middle. That's my feeling is that if it's really truly only happens once, I think humans are just as bad as anything else. Because, you know, we're pattern recognizers. This is what we are. And so if the pattern only happened once, there's just no chance. It's just that we are good at kind of manipulating and warping these patterns in a way that we can still recognize them even when they're hiding away from us.
All right, thank you very much. That was a perfect ending. Wow, so this was a really inspiring 2 days of talks. We covered a lot of ground, a lot of disciplines. A huge thank you first to the co-organizers, to Shafi Goldwasser and Michael Bronstein. And to all of you for just participating, and really everybody here really added so much to this. And so this was the Decoding Non-Human Communication #2, because we did the first one in the pandemic. So it was online. So this is the first time that this was an in-person one. And so we'd like to sort of announce that we'll do another one next year. So we'll do 3. So this will be an ongoing thing. And yeah, I also just wanted to pass to the 2 co-organizers to say a few last words.
Yeah, I want to thank everybody for coming. And I know that the plan was to have the next one in Boston, but I actually am very inspired by the hyenas, and I think we should have it in Africa. Stay a little away, but I'm not completely joking, but we'll have to talk to Daniela Rus about that. Anyway, thank you all for coming. I think it was fascinating. And I think Rob has got a lot of heat on him now with all the data acquisition, as do all of us. So thank you. And Michael.
Well, I will be brief. I think it was wonderful. At least I feel that we learned a lot. And compared to the first workshop, which was online in the midst of the pandemic, I think seeing people in person is a completely different experience. So thank you for coming.
One last thing, we started the conference, talking about Roger Payne, and through these last 2 days, the word has got out more of the legacy that he left. And I just wanted to dedicate this conference to Dr. Roger Payne, our senior advisor of Project SETI, a deep friend and mentor to many of us. And as we continue on, he was just 2 weeks ago, I was with him telling him about this project, and he was hoping to join in on the live stream, and was excited about it, and was very excited that his other very close friend Diana Reese was coming here and to integrate into this. So yeah, to Roger, who will continue on with us in memory as we continue on this journey together. So thank you.
Major thanks to David, who's really organized it all.